Hello everyone, welcome to Calculus 3 course. The code of this course is BUSFT 301. This course is of credit 2. So the list of references which I will be using for this course is as follows. The first one, Tom Apostol, Calculus Volume 1, Wiley and Sons publication of Asia Private Limited. Then second one is R.R. Goldberg. The title is Method of Real Analysis. Then third one, Bartle and Sherbert. Real Analysis, named as Real Analysis. Well, I know there's all three books are available in our college library with multiple copies. But now due to pandemic, it is difficult to take the hard copies. We'll see to it whether, if possible, we will see through college library we can make it available or not. That I will see to it. But I'll suggest you the first number book, that is Tom Apostol, Calculus Volume 1. That those who are really interested to take mathematics in final year can buy even hard copy online. That's not hard and fast timing. If you those who are interested to buy a book, they can. I will strongly recommend to take the Tom Apostol copy. So well, there are 3 units in this course. So I'll start with the unit 1, that is Riemann integration. Well, you must have done the integration chapter in your 12th standard. So you were using only integration and integration. Now onwards, instead of saying integration, I'll say Riemann integration. So why Riemann integration? Riemann was a scientist who gave the idea of integration, or who gave a concept of integration. To honor that scientist, we will say Riemann integration. Or sometimes I may say R integration, R integrable and all. So our first definition is partition. The definition is as follows. Let capital I is equal to close interval a comma b be a closed and bounded interval in R. A partition of I is a finite ordered set P, which is equal to x0, comma x1, comma x2, comma dot 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 xn is equal xn such that a is equal to x naught less than x1 less than x2 less than dot 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 less than xn is equal to b. So 2 points to be noted. The point number 1 is the starting point and the ending point of partition must be the interval points. So here the starting point is x naught and ending point is xn, is a and b. That should be very important. And second important point is this order must be increasing. Your x naught should be strictly less than x1, less than x2, less than x3, so on and so forth up to xn. So a set satisfying this condition is called as a partition. Now let's have quick example of partition. For example, so if I take interval I as close interval 0, 1, now let me write down few sets and I will ask whether it is a partition or not. So number 1, so P1 is equal to close interval 0, half, 1. Second, P2 is equal to 1 by 2, 1 by 3, 1 by, so I should write in a proper way. So let me control save. Could I able to so let me write down again the example number 1. I is equal to close interval 0, 1. So the first one, let me take P1 is equal to 0, half, 1. Second, P2 is equal to 1 by 3, 1 by 2, 1. Third is equal to P3, which is equal to 0, 1. And the fourth one is equal to P4, which is equal to 0, 1 by n, 2 by n, 3 by n, 4 by n, dot dot dot, n by n, which is equal to 1. Yes. So now we will check all this whether they forms a partition or not. So it's very simple to check whether it is partition or not. We need to check the starting point, ending point, and the whether it is in an increasing order or not. So now you could see that in this the starting point and ending points are matching with the interval, and you can see that 0 is less than half and half is less than 1. So it satisfies the both condition of partition. So this is a partition. That's correct. For the second one, you could see that here the starting point is 1 by 3, whereas it should be 0. So it is not the partition end point must be the end points of the interval. So this P2 is straight away not a partition. Why? Because if at all it should be a partition ke liye it would have been started with 0. But in this case it is not starting with 0, so hence it is not a partition. Now in the third example, you can see that starting point is 0, ending point is 1. That's fine. And you can see that 0 is less than 1, which is in increasing order, implies that it is a partition. Now in the fourth case, you could see that 0 and 1, it is starting with 0, ending with 1. That's fine. It is a starting point and end points are same as your interval. Moreover, this, where does n belongs? So here n, note that this n belongs to natural number. Moreover, 1 by n is always less than 2 by n, which is less than 3 by n, which is less than 4 by n, so on and so forth. So increasing order is also satisfying. So this is also a partition. The P4, this partition is a special partition because this partition says that we have divided the interval into equal parts. So when we say divided the interval in n parts, so such kind of partition in future we will call it as an Pn. Pn stands for we are dividing the interval into n equal parts, hence we will call it as Pn. So in future, if I use Pn, that means we are talking about the partition where there are you will have the n subintervals. Of course, this P4 has n plus 1 points because you could see that this is x0, this is x1, this is x2, so on and so forth, this is xn. So you are starting with the 0 and ending with xn. So P4 as n plus 1 points, that should be noted. Well, now my next definition is upper sum. So let f be a function from closed interval a comma b to r. So when codomain is r, then we call that function as a real valued function. So be a bounded function. Let p equal to x naught, which is equal to a comma x1 comma x2 comma dot 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 xn is equal to b. Be any partition of I. Now in this case, what is I? So this closed interval a comma b is also called as I. So be any partition of closed interval a comma b. Now we will be defining the upper sum. So how we will be defining? So I'll draw a small diagram here to explain this. So suppose I have my function over the interval a comma b. So this is my a and this is my b and this is my y equal to f of x function. Now I know my partition also. So this a is same as x naught and this b is same as x1 xn, and of course this here somewhere I will have x1, here somewhere I will have x2, here somewhere I will have x3, so on and so forth. Somewhere here I will have xi, so on and so forth. Right. So what I will be doing, I will be forming a rectangle, a straight lining. So here the last point is xn and before that there is an xn minus 1. So of course there are n rectangles I will be having. Not rectangle, I have just taken strips. Now what I will be doing, I will be taking forming a rectangle which is above the curve. Maybe my diagram is not very sharp, but I am trying to form a rectangle which is above the curve. Now if somebody asks me to find out the area of this first rectangle, what is area of this? So how will I calculate this? Area of first rectangle. So let us call it as okay, first rectangle. is equal to, so we will call that area as A1, suppose. So area of first rectangle, so the area of rectangle is nothing but base into height, so that is base into height. So here base is very clear, a to x1, so that base is basically uh, x1 minus a, but a is same as x0. And the height, see, now you can see that this has a, how to find out the height we can find out through the function. So how will you find out the height? See, you can see that the rectangle is touching the curve I have drawn with the blue, that यहाँ पे there is a, you can see that the rectangle is touching that curve. So at that point, what is the height that I need to find out? So that, let me call this as that value as m1. And what is m1? So m1 is basically my maximum value of a function, ये curve का, this curve का maximum value between the x0 to x1. But I won't be using maximum, I will be using a nice mathematical word called as a supremum. It is a supremum of a function such that, where does x belongs? X belongs to x0 comma x1, right? Now similarly, area of rectangle of area of second rectangle, I should say. So let us call it as an A2. So A2, and again I will come to the graph. So base is x2 minus x1, and the height is, again I will see the function in this. So this is my function, ये curve है. So in this the maximum value touches over here. So I supposed to find out that value. So that will give me a height. So now is it necessary that now in this case you will realize that the graph is increasing. Suppose if I take this rectangle, maybe I should change some another rectangle. Suppose suppose if I take this rectangle somewhere, let me complete this I2 and then we will talk about the in general. So A2 is nothing but again my x2 minus x1 times m1. I have used m1, but I should say m2 now. So what is m2? m2 is supremum of my function fx such that x belongs to x1 minus x2. Right, so let me have one more. So A3, if I want to write down, now you can easily guess from the graph, it will be this rectangle and this rectangle, the base is x3 minus x2 and the height is m3. x3 minus x2 times m3, where m3 stands for supremum of my f of x such that x belongs to x2 comma x3. So continuing in this fashion, my AI will represent the area of ith rectangle, which can be written as, the area will be xi minus 1 into mi. And now you can guess what is mi. So my mi will be supremum of fx such that x belongs to xi minus 1 comma xi, right? So this a1 a2 in general ai we have calculated. Now what my target is, so well, let me go ahead. Where is that? Okay, so if I find out the all these areas, so there will be a1 a2, there will be n rectangle. So if I write down the areas of all these rectangles, so let me write down those areas in general. How does it looks? So now, so that total area, so a1 plus a2 plus dot dot dot, this all area if I club, then that total area is called as a upper sum. So upper sum is equal to a1 plus a2 plus a3 plus dot 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 an, which is same as m1 into x1 minus x0 plus m2 into x2 minus x1 plus m3 into x3 minus x2 plus dot 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 dot. The last rectangle will be mn times xn minus 1 bracket complete. Right. So well, this full expanded form can be written in a compact way. So upper sum is equal to summation capital Mi into xi minus 1, where I goes from 1 to n. If you expand this, you will realize that when I is equal to 1, it will give me m1 times x1 minus x0 plus m2 times x2 minus x1 plus m3 times x3 minus x2 plus m4 times x4 minus x3 plus dot 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 dot. The last term will be mn times xn minus 1. And this upper sum is denoted by upper sum is denoted by UPF. So UPF stands for upper sum of a function f with respect to a partition P. Right. So again I am telling what is UPF. UPF is a upper sum, but it has a meaning. The meaning is it is a upper sum of a function f with respect to a partition P. And now what is mi here? Let me write down that mi, though I have written, but still I wanted to write again. So it is supremum of f of x such that x belongs to your xi minus 1 comma xi minus 1 comma xi interval. So maybe since I don't have a space, so maybe I hope you will understand what I wanted to write down here. So I can minimize my font size. So let me write down a remark. Geometrically speaking, UPF represents sum of areas of rectangles which lies just above the function, because you could see that we have seen via graph also. In this graph, the area of the functions, those rectangles which lies just above the curves, right? So when we form a rectangles above the curve, and when we take the areas of all those rectangles, then the accumulated sum, the total sum, is called as a UPF. Now, of course, one may ask that one can have an area below the curve. So when we take the area below the curve, that area, that total area, is called as a lower sum. So now this gives me a space to define a lower sum now. Since I have talked about what is UPF, roughly speaking, it says that it is an areas of a rectangle, sum of the area of rectangles which lies just above the function. Now we will define lower sum. Right. So I hope you have understood what is upper sum. On similar line, we will define lower sum. So let f is a function from I, which is closed interval a comma b, to r, be a bounded function with a partition p which is equal to a x naught comma x1 comma x2 comma xn equal to b any partition of I. Now let me draw a function. Now let me draw where is x naught, which is a, and this is my xn, which is my b, and this x1, x2, dot 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 dot. So somewhere here I have xn minus 1. Now again we will form a rectangles now. Now this time when we are forming rectangle, it will be below the curve. Now on the same line, this will be. So basically I am interested in this area. So now area of rectangle 1, area of first rectangle, that we will call it as an A1, which is equal to. Now you realize that the area of a rectangle is base into height. Now base is very clear, it is x1 minus x0 times the height is now that will be best because of function. So now you know this horizontal line touches the function here, and basically that is the minimum value basically. So this curve, now the blue line which I have shown, that blue line, that my, and now I will show you the green line also. Now you can see that my green line touches the minimum part of that blue line. That blue line is basically my function. So I can find out the height with the help of function. So now I will say into m1. And now what is m1? Now where m1 is my infimum of my function fx, such that x belongs to x0 comma x1. So in this interval, whatever in this interval, my function's minimum value, that is basically here it is infimum, that value is basically my height of first rectangle. So the area of first rectangle is a1, is denoted by a1, which is x1 minus x0 times m1. Now if I go to the second rectangle, now again I will show you, second rectangle has my function has a curve like this. And now how to get this height with the green line, I will show you that my rectangle meets at the minimum value over that green line. So now I will define here again. So area of second rectangle, I should say, is equal to, that we will denote it as an a2. So it is x2 minus x1 times small m2. What is small m2? Small m2 is infimum of my fx, such that x belongs to x1 comma x2. So continuing in this way, my ith rectangle, area of ith rectangle is nothing but ai, that will be small mi into xi minus 1. Well, where small mi is equal to infimum of my function fx, such that x belongs to xi minus 1 comma xi, like that. And now what is lower sum? If I accumulate, if I combine, add all these areas, then I will get the lower sum. Lower sum is equal to a1 plus a2 plus a3 plus dot 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 an, which is same as small m1 times x1 minus x0 plus small m2 times x2 minus x1 plus dot 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 the last time small mn times xn minus 1 bracket complete, which is same as I can write in a compact form. I goes from 1 to n small mi xi minus 1. What is small mi? Small mi is infimum of my fx in interval xi minus 1 comma xi. This is what my lower sum, and lower sum is denoted by L P F, capital L, capital F, sorry, small f. So LPF formula is summation I goes from 1 to n small mi xi minus 1. Similarly, we had defined UPF, which is equal to summation I goes from 1 to n, and there we had a capital Mi. That capital Mi was supremum of a function over the ith rectangle. Now here again, roughly speaking, geometrically speaking, LPF represents the sum of areas of rectangles which lies just below the curve, or you can say that curve of a function below the function. So now it is very clear that I hope in this lecture you must have understood UPF and LPF. Now our target is to find out the exact area below the curve, the integration a to b f of x dx. That meaning of this geometrically is the area of the function below the curve. Now you can see that whatever I have done, whatever UPF and LPF I have defined so far. Let me show you those. Now here when we have shown, now you can see that lot of error is occurring. This is not exact integration. LPF is not exact integration because you can see that this area is missing. LPF, this area is not covered. So this whatever area we have, because our target is to define overall integration, but when I want to define that, so you can see that this sum of the part is missing. So maybe let me delete this part immediately, because I will be sharing this PDF also with you all, so there should not be ambiguity later on. So that's fine. Yeah. So my target is we wanted to find out the exact area below the curve. Now you can see that in lower sum, some of the area is missing, whereas in upper sum, some extra area has come. So intuitively, or you can visualize your integration answer, whatever integration is between UPF and LPF, because UPF gives you extra area, because when we have drawn the UPF at the time of UPF, we were taking the area of the rectangles which are above the curve. Now you can see that in a UPF this extra part were coming. Similarly, this extra part was coming. So in UPF it was an addition in an area, whereas in LPF it was a deletion, and you were not getting exact area below the function. So my point to explain is, it should be very clear that your integration value, let me write out that, you can observe your integration value a to b f of x dx. Of course, it's a number. This is gonna one number. This number is always lies between LPF and UPF. That one can easily generalize. Well, if you are unable to generalize, visualize, then we will speak about this in lectures further. Thank you. In upcoming lectures, I will be taking a problem based on UPF and LPF. Thank you. Thanks a lot.